Ahead and get started, and your mics will be live. I'm going to leave it going for about, I don't know, 10 or 15 seconds, and then we'll start. When I start talking is how you know we've started.
Oh, that's not good.
Thanks, Harley, for putting in that little audio bit there before I went live. Hello, everybody, and welcome to this week's Future in Space Hangout. My name is Tony Darnell from deepastronomy.space, and that person you heard saying that's not good is what we don't hope to hear in the coming months when we talk about our topic today, which is the Parker Solar Probe. NASA is getting ready to launch a probe that will go very, very, very close to the sun, and the way they're building it is it's going to actually touch the sun, but you know what? There is no hard boundary on the sun, and it's kind of got a very layery in there, so it's going to get closer than we've ever been for sure. And it's going to be launched in a couple of months. Now, just last night, we're coming off the tails of a really successful launch by SpaceX on the test mission. So I'm still kind of jazzed about that, very excited about that. And now we get to look forward to another big mission coming up here with the sun, with the Parker Solar Probe. And my guests today are from that mission, and they're going to help me discuss it a bit. Let me bring them up. And for those of you who we are streaming live, and I hope that you will interact with us and ask our questions via two main ways. There's the live chat on YouTube, which you'll probably end up using the most. But I also have a Discord server that you can interact with. If you go to deepastronomy.space/live, you can chat right with us there on Discord. I've got both things up. I see John Suffles on Discord, so that's good. And ask our guests questions about what we're going to be doing with the Parker Solar Probe. So let me introduce my guest down. First off, my co-host, the guy who goes, well, that's not good. Oh, by the way, Harley, a couple things. Turn off your
Don't say that again.
Turn off your email notification before I get any further.
It's been turned off.
Thank you. Dr. Harley Thronson is down at the bottom panel. He is from NASA Goddard. Hi, Harley, and welcome.
Hey, good afternoon. At least here on the East Coast. Good afternoon.
Yeah. And it's still, well, it's East Coast it's afternoon now in the West Coast too, isn't it? It just turned that way. So anyway, good. Thank you, Harley, for setting. Harley is the guy who helps us set these up and gets the guests for us. And today our guests are in the upper right panel is Dr. Phyllis Whittlesea. She is a member. She's a professor, I think, at the University of California at Berkeley. And
I'm a postdoc.
Apologies. I usually ask before I start, and I didn't this time. Dr. Roberto Levy is also right next to her in the upper left panel, also from the University of California, Berkeley. Welcome, guys. You're working on the Parker Solar Probe. Who wants to give us a little bit of an intro into the mission itself?
Well, actually, what we'd like to do is hear a little bit about the two individuals. A little bit of a bio, then introduce a little bit of a bio about the instrument itself.
A bio about okay.
Yeah.
Yes.
So, Roberto.
Yes.
Who are you?
Yes. Okay. So, hi. My name is Roberto Levy. I'm a postdoc at the University of California, Berkeley. I did my undergraduate at the University of Maryland and my graduate school at the University of Texas in San Antonio. And I have worked on several different missions. I started working on the Cassini mission at Saturn, and followed by the MAVEN mission at Mars. And now I was finally able to do some instrumental work with the Parker Solar Probe, which is now in Florida, as has been mentioned. But that's sort of a summary. So.
Okay. And Phyllis?
Yeah. Hi, my name is Phyllis Whittlesea. I'm at the University of California, Berkeley. I've worked on solar probe in one form or fashion or another since graduate school. I went to undergrad at the University of Texas at Arlington. Back then I was doing data analysis using some already pre-existing spacecraft, so like the WIND spacecraft, L1, GeoTail. So were launched in the sort of mid-90s. And then I went to graduate school and I got to work on building up some calibration facilities and plasma sources for the solar probe Faraday Cup, the Solar Probe Cup. Currently, I'm the instrument scientist for the span Electron Instruments that are on Solar Probe, And I should point out, Roberto's the instrument scientist for the SPAN ion instrument. He doesn't give himself enough credit. That's our short history.
SPAN electron. Well, I will get to those in just a minute, but we'll talk about what some of the instruments are. Okay, Harley. Well, since we're in
now.
What else can I do, Harley? Tell me what to say next.
So let's get started. And then now
can I get started?
So let's get to the overview. And I think Roberto was going to speak up and describe for us the mission, its science goals, top level description of this really exciting mission.
Yes. So Parker Solar Probe will launch in July 31st, and it's going to be the spacecraft that's going to touch the sun, as we say, or the spacecraft that's going to get the closest to the sun that we've ever been. And the ultimate goal is to essentially observe pristine solar wind, or solar wind that has not been yet perturbed as it is expanding outward. This will be the first time that we will make these measurements, and there's going to be very new and exciting science that we hopefully have never seen before. So it's going to be full of surprises. That is a general outline of the mission from a particle point of view. Maybe Phyllis can talk more about the fields. Or
Oh, yeah. Okay. Sure. So Solar Probe has a couple main science objectives. Actually, the history of Solar Probe is kind of interesting. The concept's been around since before NASA was actually incorporated. Before NASA, there was this, I think they call it the Simpson Committee, and they identified several different missions that we should have to do science in space and, take advantage of all these new rockets that they were coming up with. And one of them was, like, let's send a probe to Mars. Okay, well, we've done that. Let's send a probe to Venus. Okay, we've done that. And then, so on and so forth. And then they wanted to send a probe to the sun to try to figure out why the sun, how the solar wind gets accelerated, why the solar corona is millions of degrees, but the surface is only 5,000. And we haven't actually had the technology and the engineering to do that until recently. So from that perspective, I think Solar Probe's a really interesting mission. That the idea has been out there for a long time. And we've had these questions for a long time, like, how do we accelerate energetic particles that come out of what we think are CMEs or solar flares, or maybe not?
Yeah, CMEs are coronal mass ejections, just so you can clarify that. Yep. Go ahead. Was that it?
Yeah.
Okay. All right.
Well, so okay. Yeah, I mean, I could go on ad infinitum. So.
Okay. Well, I just wanted to make sure I didn't interrupt you. So
No, you're just fine.
Okay. So, it's funny that you mentioned that, because it's, we talk about these missions that have been on the drawing board for a long time. The Hubble, it's the same is true for the Hubble Space Telescope, before it was ever launched, things like that. But we're finally now, is it because technology is getting to the point where we can do these things, or is there just a political will now, or a scientific driver for it? What's the main motivation, do you think? That we've been talking about these since before there was even a NASA. So what makes you, what do you think gets these things built now?
Well, I think it's really a matter of having the technology and the engineering to make it happen. Right. So a big issue with Solar Probe is, since it goes so close to the sun, within 10 solar radii from the sun or 9 from the photosphere, is you have to have this heat shield to be able to stand the intense temperatures. So over 2,000, 2,500 degrees C. And you have to figure out how to make science instruments that can withstand that environment as well. And it's definitely not easy. So if you look at past iterations of the Solar Probe mission concept, there are these funny, like, conical shields.
Here, I'll put it up. You gave me a picture of it. Let me put that up real quick.
Yeah, so this is like an old version, right? Yeah. That's like the old Solar Probe that was actually powered by an RTG, I think, if I'm not mistaken. Sort of funny. You go to the sun and well, we can't use solar power because we can't make solar panels to stand the solar illumination. But that's the old concept. I have a bunch of new pictures of the spacecraft. Now our heat shield is flat, and it's some sort of fancy carbon foam, and we have sun sensors to keep it aligned.
And I'll put those up here in just a bit.
So
but first,
I think at this point it's important to point out that the heat shield is always pointed towards the sun to keep the instruments safe. That was the idea back then. That is the idea now. It's just the shape of the heat shield may have changed. And of course, other technologies have advanced since then.
Definitely makes sense. Well, before we get that far, we haven't really talked yet about the launch and how it's going to get put up there. So let's talk about that now. What is the current date for the launch?
So the current date is July 31st, and it's going to be a 4 a.m. night launch this year out of Cape Canaveral. And yeah, it's going to use a Delta IV Heavy, which you're showing right now, I think.
Yep,
yes.
I am.
That's right.
So this will be an impressive launch. I can't wait to see this. And it's going to also be very early in the morning at 4 a.m., I think is what they're nominally targeting. So it'll be dark outside, but it'll be spectacular because night launches always are. Yeah, it really will. So coming up, July 31st, just a few months after the great launch of TESS we had yesterday, we'll be having this launch go up. Now, it is nominally going to, let me see. Okay, we'll talk about how it's going to get to the sun. So now it's launched. It's up there. It's going up on the Delta IV rocket, and it's actually going to take a long time to get to the sun, isn't it? You want to talk a little bit about the trajectory?
Yes. So the trajectory, it's going to launch. It's going to. You can see at the bottom left corner. You see the first Venus flyby September 28th, 2018. So it's fairly soon after it launches. After that, there will be another 7 Venus flybys or gravity assists to lower us into a closer orbit to the sun. And this, the first, I guess, closest approach to the sun, the first perihelion, will happen on November 1st, 2018 at 35.7 solar radii. And hopefully, and then soon, several years later, I think 4 or 5 years later, we will have our closest approach or our first minimum perihelion within 10 solar radii, which will be the most exciting time, I believe, in the mission.
Right. So this thing launches in July. You can see the little red line. I can't use my pointer here on this particular way I'm doing it. But the launch it's coming out first. It flies by Venus, so you're shooting it basically at Venus. It goes around. That'll be on September, a couple months later, and then that's going to change the orbit, the trajectory of this spacecraft, such that it falls into this weird orbit around the sun that we're showing in the red here. And the first time it gets the closest will be in November, the following month of the launch. And you were just saying that this shield has to be pointed absolutely perfectly at the sun all the time, right?
That's correct. Yes.
What kind of tolerance does this thing have? I mean, what if you're off just...
It's extreme. It needs to be extremely precise. We're talking about within a degree of precision. Any sort of deviation from that could cause the instruments to fail. And if they fail, they could cause other instruments to fail. And it would just be this horrible chain of events. Therefore, the attitude control of the spacecraft is crucial at all times.
And so it will be pointing the shield at the sun throughout this multi-year, multi-flyby activity. And of course, especially, or probably throughout the trajectory, but presumably especially at its closest approach, at its perihelion.
And this will be coming in at about 35.5 solar radii, it says here. And
yes, that is the first perihelion.
That's right.
Yes.
And yeah, we have 24 of those.
Yeah. Why is it taking so long to get where you want to be? Why is it taking 7 years?
It's really not very easy to get that close to the sun. So, we have our, I mean, part of this, I think the original solar probe design was quite different from this. And this orbit was designed so that we could maximize the science over the longest duration possible. So we go into like our prime science phase 10 days before, or 5 days before perihelion, and for 5 days after, we remain in that science mode. So it's difficult to get that close to the sun. It takes us having an encounter with Venus 7 times in order to get that close.
Yeah, and why is that? Just because it's it's an inner orbit of the spacecraft. We're coming from Earth, so we're going at a certain rate around the sun, and we need to change all of those parameters, the rate at which we're orbiting and the trajectory and pointing. Would it take a lot of fuel to just manually have rockets turn you? Was that the problem with getting in the right orbit right away? It just would take too much rocket fuel?
Well, I certainly imagine so. I mean, if you look at the Delta IV Heavy, the top part where we mount the spacecraft, inside that's the fairing is what covers the spacecraft. And it's this huge empty space Yeah, so just the top part up there is the fairing. And our spacecraft is very small. It's only like, I think, 2.5 meters tall and 1,000 some odd kilograms. I don't think it's very heavy. It's pretty small for a spacecraft. So we don't really have very much space for fuel. Our fuel tank's only a couple centimeter little sphere. And I would assume that that's right, although I didn't really participate in designing this orbit.
Well, I was just curious about why it takes so long and it's such a big deal to get anywhere inside the inner solar system for these probes. Mercury, it was the same way when we had Messenger going there. It took a long time to get there. So now, but it sounds like you're going to have an opportunity to use those 7 years en route. Each time you fly by Venus, 7 times you said, will get us just a little bit closer to the sun with each passing encounter. And then all the while, this thing is pointing directly at the sun, and presumably all of the science is getting done while you fly in. So I want to talk a little bit about some of the instruments that are on board, but before I do, we got to talk about the heat shield, or what are you calling it? The thermal protection shield, right? That's the thing that is keeping this thing from blowing up. What is it made of, and how is it like the solar tile, or the solar tiles, the space shuttle tiles?
Ceramic.
Ceramic.
Yeah.
Thank you. Is it like what's it made of, and how does it work?
So I know that it's made out of carbon foam. Personally, I don't know what carbon foam is. I just know it's very heat resistant. Yes, that's as much as I know about it.
Okay,
Right.
so
Yeah.
Go ahead, Phyllis.
No, I think so. I know they're actually sort of keeping the brew of this thing a bit of a secret.
Really?
It's, I think it's some sort of special technology, but I don't actually know. That's my guess, because I haven't actually seen any presentations on the specifics, but I know that it's some sort of fancy carbon foam. There's like a layer of, I've seen a sample of it before. It's got like a layer of carbon fiber on top of it. And then I think they're coating the whole top of it in some sort of thermal coating. I want to say it's either like alumina or some sort of thermal coating on top of it. But they're very protective over the heat shield. Like most of the testing that we do with the spacecraft, the heat shield is not on it at all. It's locked away in some special container.
Who's building it? Is it a proprietary thing for the contractor, or is it NASA that's keeping it secret?
Oh, I think it's more just a concern of it getting damaged, really.
Oh, I see what you mean by okay, but not talking. It's not like a secret to see it built, or any of that, because that doesn't. So. Yeah, that's not how NASA rolls. I didn't think so. Okay, well, okay, so this has the same role as the sun shield has on the James Webb Space Telescope. Only this has got to work in a much more hostile environment, I think. The idea with James Webb Space Telescope is to get the instruments down to about 30 Kelvin. Here, you're trying to protect the instrumentation from getting the full brunt of the solar radiation. What is the temperature difference between the side facing the sun and where the instruments sit? And what would be the operating temperature of the instrumentation?
The operating temperature of our instruments needs to be below 40 degrees Celsius.
Wow, really? So
yes,
that's pretty.
So
yes, that's like room. That's almost like a hot
Celsius.
day, and that's a hot day in Spain or something, right? Well, I'm really hot day.
Well, not compared to the front of the spacecraft.
Yeah, no, that's much hotter. Yeah.
So wow. So that would be that's quite a temperature differential. So and does it? I don't think we have a picture of the shape of it, do we?
Yeah, we should be showing a picture of the.
Well, I'm trying to find one. I got a lot.
That's it, all wrapped up.
Hang on just a sec. Let me get this to go away and this to go away, and let me. So that's it, all wrapped up. Do I have a picture? I don't think I have a picture of the whole thing. Do I?
I think the website, the Solar Probe website, I think has got an artist's conception.
Okay.
Of the
well,
thing.
Harley, if you want to get one for me and share your screen, that'd be helpful. I didn't bother to get one for the whole spacecraft, but these are some of the instrumentations that we're going to talk about here in a bit. But okay, so the the whole idea of the shield is going to be to keep the instrument to protect it, and you were saying that it has to be precisely oriented because any slight variation would give just even a part of the instrumentation, the instrument package, a blast of the solar radiation, and that would fry a great many things.
That's correct. Yes.
What about radiation hardening? And I mean, is the surrounding, does it also blast all of the radiation? I guess of the high energy stuff like gamma rays and X-rays and all of that stuff. Does it protect from that as well, or just is it just thermal? Sounds like it's just thermal.
So I think its primary function is mostly thermal.
Yeah.
I don't think for the really high energy stuff, for really energetic particles, there's not a whole lot that you can do to block them. Like, for example, on Juno, I know they went to a great deal of effort to make these vaults where they have most of their electronics, which are really just essentially thick metal boxes to try and stop these energetic particles from damaging the electronics. Okay. So the TPS is mostly for thermal. Okay. Although I should point out there are 5 instruments that are actually in the sunlight as well. Most of the instruments are in the shadow of the heat shield, but there are 5 of them that are actually out in the sun and experience that harsh environment as well. And there was quite a bit of engineering necessary to get that to happen.
Got it. I think we were talking about why it takes so long for these missions to get actual realized. This is part of it. Material science. I mean, I would imagine carbon foam certainly wasn't around in the 50s and 60s, and the kinds of hardening that has to happen for a lot of this instrumentation probably just didn't exist. And again, I go back to James Webb Space Telescope. They had to invent materials to be able to be lightweight enough to hold that giant primary. So, it made that telescope and others are not possible with the technology of the time. And so now we're getting things really lightweight to the point that we can do these missions. So let's talk about some of the instruments then. So you guys are working on the, I think you call them span instruments, or maybe you could talk a little bit about the instruments that you guys are working on and responsible for. And maybe we'll start with Roberto.
Yes. So we've been working on a suite called SWEEP, the Solar Wind Electron, Alphas, and Proton Suite. And it's essentially a particle instrument suite, a plasma suite. I personally worked on the ion side of this instrument suite called the SPAN AI. So SPAN stands for Solar Probe Analyzer, ion. And what these are electrostatic analyzers or curved plates that can essentially select out different energies at different time intervals. And with that, over time and over integration, we can develop velocity distribution functions, from which then we can also derive properties of the plasma, such as densities, temperatures, and velocities. One more component that the ion instrument has is a mass discriminator, or a mass analyzer, rather yet. So not only will we get the information about what the plasma in general is, but we will also have information about what species it is that we're looking at. And specifically, we will be looking at protons and alphas, or doubly charged helium, which are the main components that are coming off of the solar wind. And this is sort of a summary of the ion instrument, but we also have 2 electron instruments, which I'm sure Phyllis can elaborate on.
Yeah, I think I'm showing them, aren't I? I don't think I'm showing the right thing.
Yes. So on the left, what you're seeing right now is SPAN A. On the left side, you have the electron instrument, and on the right side, the ion instrument. Okay. So yes, this on the right side is the instrument that I was just describing, the ion instrument. Okay. And the metallic, or the titanium little circular part on the right side that you see right below the hemispheres is the time of flight section of the instrument, which will help us differentiate all the different masses.
Yeah. So essentially what these things do is they map the direction and the temperature and the density of these particles, right? Whether it's ions like protons and alphas and charged states and whatnot. For the case of the ion instrument, in the case of the electron instrument, it's electrons. But they're sort of mapping it sort of like, pixelating the whole sky and measuring in pixels what the density and temperature and speed of those particles are. So the electron sensors, I'm just going to segue. The electron sensors are also electrostatic analyzers. They have a field of view. It's like plus or minus, what is it? Plus or minus 60 degrees up and down. They have a 240-degree field of view, and their two fields of view combine like that's an image of the instrument in test, which is a long and extensive procedure. But the two fields of view for the two electron sensors, they're mounted on either side of the spacecraft, and they come together like the two pieces of leather on a baseball. So you can think of each piece of leather as the field of view and instrument of one of the electron instruments, and then together they get a full sky measurement of the electrons in the solar wind in this sort of coronal plasma near the sun.
Wow, these things don't look very big from these pictures. How big are they?
They're not that big. I would say about half a meter. Okay, meters.
Yeah, that's fine. Half a meter.
Yeah, about
maybe a foot in size,
half a meter's fine. Yep.
Yeah, foot in size roughly.
Okay.
But these are two instruments, so each would be half of that.
Yeah, you can basically take it and cut it in half, where you see all those slices which have electronics boards, and you have two separate instruments. We bolt them together and mount them on the RAM side of the spacecraft.
Okay. So why don't we talk? So I wanted to talk a little bit about the testing procedure. You said this was this was it in testing. What was that like? What did you do what was the testing done on this for?
This is the Electron instrument?
Well,
it looks like the Electron instrument.
Yeah, I think it is.
Can you see it? I'm not sure which one it is.
Yeah, so in this particular instance, we're firing electrons in a vacuum chamber. So this is a picture taken through the window of a vacuum chamber. Fire electrons at the sensor and move it across the full field of view to test and make sure that our calibrations are actually correct. Either before or after this picture was taken, it went through environments testing, which is where we put it in another vacuum chamber somewhere and cycle the temperature up and down for the expected temperature range that the instrument will see and make sure it still works. Often in this procedure, something doesn't work as expected, so you have to pull it apart and fix it and put it back together again and then try again. And before that happens, you wind up having to vibrate the whole instrument on a vibe table to simulate the launch environment. It's not a very easy ride to space.
Okay.
So long and extensive testing process before these things actually get mounted on the spacecraft. And then when it's on the spacecraft, you do the whole process all over again.
Exactly. I know, right? By the time it's gone through, you've gone through quite a few tests of what it's going to actually be like to be out there. I'm always worried about wear and tear on the instrumentation by the time you've gone through all these tests. But I guess they've got it down to a system where they know.
Well, that's absolutely a concern, though. If we have to repeat tests, which we had to do, there is always a question of how often can we test it before we start getting the wear and tear, as you mentioned.
Yeah.
So that's definitely a concern.
It's been hard for some of the sensors on the spacecraft. Like another instrument that's part of our particular suite, which is the solar winds, electrons, alphas, and protons suite. It's designed to measure the particles in the plasma. The sweep suite, say that 3 times fast, has a Faraday cup, which is a little small sensor that also measures particles. It sticks sort of like on an arm around the heat shield and directly in the sun. And there was a bit of contention because all of the materials that are in this instrument have to do things like withstand high voltage, stand off high voltage from ground and not melt, which is an issue. So during that qualification process, there was a bit of debate as to whether you do the exact same sort of thermal qualification. You know, this thing's going to see thousands of degrees. Do we really want to do that? Make it see, vibrate it, make it see thousands of degrees, which could change the material properties, and then put it on a spacecraft where it's going to do it again? That's just not really a good idea.
Yeah. So you said this was
when exposed to high temperature.
You said this was a Faraday cup. Is that what you used? Is that what you said? So it's a little cup.
That's right.
Out of a little.
Yeah, it's tuna can sized, but it's got a heat shield that's a little bit bigger.
And you stick it out into the solar stream where.
Yeah, it's just clinging onto the side of the spacecraft for dear life. Yeah, that's right.
So I'm hearing a lot about sensors, and you're measuring particles and electrons, plasmas. Do you have any detectors? Are there any cameras on this spacecraft?
There is a instrument called Whisper. That is a white camera, but that's as much as I know.
Yeah.
So Whisper, I think it's actually made by the same people that build coronagraphs. I think at NRL, that's right. So it's a white light imager, and normally these white light imagers sort of image the sun from far away, like at L1 or where stereo is, Earth distances. But Whisper is actually mounted on the RAM side of the spacecraft, so it's watching the plasma that the spacecraft is about to plow through. And I think the idea with WHISPER is that it's like taking sort of like a CAT scan of the plasma as it flies through the plasma. It's a really weird mode for that type of instrument. I think it's the first time what we call like a remote sensing instrument that's meant to look at things from far away is being operated in situ in the actual plasma. So it's really novel.
Yeah, and I think that's important to emphasize with this mission, because most spacecraft that we imagine going out into the solar system and looking at things like planets, and Roberto mentioned he worked on Cassini. We want images, we want pictures, there's stuff to see with cameras, but here we're going to a place where really in situ observations are the most important thing. We've got images of the sun everywhere. We've got SDO up there. We've got stereo. You've already talked about. We've got SOHO still taking pictures of the sun. But what we don't have is anybody going out there and poking at it and measuring. Getting a thermometer and actually reading this stuff and getting magnetic field instruments, plasma detection instruments out there. And that's really the emphasis of this mission. It sounds to me like, because pictures aren't going to be as important as what you're actually physically measuring there. Am I right?
That's right. We're actually going there to like sort of, it's a bad analogy, but smell the plasma and actually poke and touch it and not just look at it from far away.
Yeah, because we've inferred a lot of these observations from looking at other things. When you look at a coronal mass ejection, for example, let me put that diagram up real quick. If we look at a coronal mass ejection, which is a magnetic eruption from the sun, we are seeing the plasma and the magnetic field lines. We're inferring those by looking at what the surrounding plasma and charged particles are doing. When we see a CME, we're looking at the effect the magnetic field is having on the surroundings. Here, if we flew right through a CME, we could actually physically say, wow, this is what the magnetic field is like. This is what the plasma flows are like. This is how thick the shock fronts are. And exactly, I mean, you get that numbers exactly, right?
Yeah,
yes, you got it.
Not only that, but since we're going to be the closest mission to the sun ever, we're going to see all these different phenomena that you mentioned at their birth, essentially, at their most pristine time. What we observe at Earth is a CME, for instance, that has gone through several different processes of energization or loss of energy. And to explain all of these different phenomena or different energy changes, we need, or it would be crucial to have measurements as close to the sun as possible, or as early in time as possible as they're just being generated. So that's another big important step to take.
Yeah, and so I think Special Eddie EDY. I think that there was a chat on the chat thing where you had said, Tony, ask about not using a mirror, please. I think that's what you meant, right? Because there isn't really a place imaging, collecting photons via a mirror. Is not something that this thing is really designed to do. Are there mirrors on the Parker Solar Probe?
Not that I'm aware of.
Yeah,
not that I know of either.
Yeah.
We have sun sensors, which check to make sure the spacecraft's pointed right, but I don't think they use mirrors.
Which actually brings up a good question, and thank you, Phyllis. I was going to ask this. So we spoke before we went live, and I was really impressed at the precision required to point toward the sun, so to protect the instruments by the shadow of the sun shield. So how does it know, since I have this right, you don't have any sensors to look at? Do you have sensors that look at the edge of the sun very, very carefully? Do they peep around briefly around the edge of the sun shield?
Right. Yeah, there are sun sensors. I'm not sure if their nominal mode of operation is to stay illuminated or if it's to be in the shadow. I assume it would probably be to be in the shadow and check for the limb of the sun peeking around the heat shield. As I'm doing like this gesture, thinking I'm doing my interpretive dance.
Yeah. Solar dance.
Right, so I get it. So they're sitting there somewhat passively. If they get a little blast of sun, then they know, oh Lord, quick, start correcting that.
Yeah, and then we had to use reaction wheels or thrusters to reorient the spacecraft correctly.
Oh, I was going to ask about that. So it's reaction wheels then?
It's both, actually. We have reaction wheels and we have thrusters as well. We hope to use the thrusters as infrequently as possible because these thrusters create little bursts of gas, and that actually they can get ionized and disturb the plasma that we're trying to measure. So that's why we primarily use the reaction wheels. And when the reaction wheels get saturated, then we have to use the thrusters.
Okay, I want to take a quick break here and remind everybody you're watching a Future in Space hangout. These are hangouts we have every Thursday. The Future in Space hangouts are done on the first and the third Thursday of every month, where we talk about a variety of astronomical or astronautical and space, the future and space flight topics. And I want to thank our sponsors, the American Astronautical Society, for providing this service to its members and to you as well. And I don't know, Harley, do you want to say a couple of words about our sponsor on this, or?
Oh, the American Astronautical Society very kindly has been sponsoring this. I think we are in the second year of this. And the motivation is to bring to the literate public, folks who follow science and engineering and technology closely, a up-to-date instruction and education and preparation for some of the most exciting missions in our understanding of the major space sciences.
Right, and in today's topic, we're talking about the Parker Solar Probe, which is a probe that is being launched later this summer to go almost directly at the sun, and we hope to learn a lot about it. We've been talking a lot about how it's going to get there. It's going to be using Venus to help assist and change its trajectory such that it gets to the closest approach it's ever going to have, which was less than 10 solar radii away in 2020, in 7 years from now. So
2024, Christmas, getting close to the holiday season, 2024.
Yes.
So folks should start noting their calendar. We'll probably be hearing quite a bit about it.
Yes.
In about 6.5 years, which leads to, we talked a fair bit several minutes ago about the multiple Venus flybys to adjust the trajectory and speed to bring it closer and closer to the sun. So the closest approach will be, as we were saying, holiday time 2024. So can you describe then perhaps not in detail about the individual observations, so it will be in some kind of complex, but maybe vaguely elliptical orbit around the sun for some period of time, observations being taken. Do you, again, we were talking about this earlier, do you have an estimate of how long that the mission ideally will last in its closest approach? And what is the nature of the observations? Passes behind the sun, as you talked about. It will be able to download data for brief periods of time or maybe extended periods of time when it's visible from Earth. So tell us a little bit about the observational operation. That's the word I'm looking for, the operational sequence in late 2024.
So late 2024 will be, as you mentioned, our closest approach. So from a particle point of view, specifically from the ions, we will never actually see the peak of the solar wind distribution. That will be the Faraday cup that will measure those particles. The SPAN AI instrument will measure the surrounding particles, or the outer edge of the velocity distribution function. And the process or the operation that will happen then is to cross-calibrate between instruments. So the Faraday cup will make one measurement, I will make another one, and once we have the data back on Earth, we will have to do a lot of data analysis in order to merge these two data sets, and from then get a complete picture of what is happening at closest approach. And I assume it's very similar for the electrons, where you have to stitch everything together in like a baseball. Is that correct, Phyllis?
Yeah, the electrons are a little different because they're just really hot. Like the temperature is really hot, so the thermal velocity is larger than their bulk velocity. So they just come in from everywhere, which is why we need two of them to see the entire set of electrons. Right.
It's an all-sky instrument.
Well, it's a composite all-sky instrument with the exception of the little area where the heat shield is. We don't want to look directly
course.
For thermal self-preservation reasons, we don't want to look directly at the sun with these sensors, but everywhere except for that. So I think we cover greater than 95% of the sky.
Where are we right now, guys, in the solar cycle? Are we near a minimum, or
we are getting out of a minimum, I think,
and we're heading up to a max?
But it's been a very
this is a weird solar cycle.
It's been very weird.
In what way?
Very weak, especially because we were trying to make some good observations at Maven, and we were waiting for a good solar storm to bring in nice phenomena, nice events, but it rarely happens. So the sun is really weak right now.
But we are on the ascending portion of the solar cycle, and by the time the Parker Solar Probe gets there, it will be more active, presumably, than it is now. Does that worry? I mean, obviously, you think about this when you design a probe to go so close to the sun, but it has to be pointed so precisely. Are you worried, or is there? What kind of effect would a solar storm? Let's say a CME goes off right below it, or it runs right into one.
So I don't think, the pointing has to always be accurate. That if that's off, the instruments might fail. But if we are inundated with a CME, the one thing that the ion instrument is that we're a little bit not worried about, but that we have to look out for is the rates that we will measure. If the rates gets too high, if the rate of particles that hit that land on the instrument is too high, our electronics are going to have a hard time keeping up with it. So those are some of the problems that we've been thinking about.
Yeah. I think part of the reason we have this long extended mission is because we actually want to increase our chances of being there when a CME blows off. Like that was part of the mission design.
For taking so long to get there, you mean? Yeah.
Yeah. So we want to increase the amount of time that we're there close to the sun so that we can actually sample a CME. And so the spacecraft was designed to handle that. Maybe not a ton of them. So if for some reason we have this astronomically fierce solar maximum, then it would probably have some radiation wear on the spacecraft, I would assume, but it is designed to handle that. So we want to measure a CME.
Well, will you be observing, I'm an astronomer, so observing, but you don't really observe in the astronomical sense. Cat behind me, that's midnight. Yeah, exactly. One of our mascots, and we were already talking about the yellow ducky. Will you be taking data on the way to your closest approach?
We're still discussing when to turn. The best thing would have been to get data when we do Venus flybys. That would have been the most interesting thing. But I'm not sure if operations will have instruments collecting data at that time or not. It's something we should certainly wish for, but I'm not sure if that's going to happen.
It's limited by two factors, right? One, the spacecraft is very, very complex, and keeping it pointed in the right direction to make sure it doesn't melt is something that's in all of our best interest. So, when we're doing things like having Venus encounters, most of our telemetry that comes through the DSN, right, Space Internet, I think a lot of that goes to the spacecraft people because they want to make sure that everything's lined up exactly right. And we really want them to as well. So I think we're primarily limited by the number of DSN contacts that we get and our bandwidth at the time. So DSN whatever our bandwidth is, however many contacts we get, we'll fill that bucket up.
Right. So actually, and once again, out of ignorance, and then the question is, when you are at closest approach, when you are really observing like crazy, you are downloading data to the Deep Space Network, the DSN. You guys dominate one of the antenna.
I certainly hope so.
Right. So therefore, the point I was getting is that presumably, and I've heard this from my Mars colleagues and so on, that that there is limited. Those are wonderful systems out there, but a lot of competition from other missions to use it. You all, the Parker Solar Probe, will have first call on the antenna when you're at closest approach, and so that you can't be using the antenna a lot as you make your various Venus flybys. I have that about
That's
right.
true too. We're limited by that as well. Yeah.
Yeah. So once again, a question that I was asking a lot of folks may wonder about: how will the mission end? What, in your estimates, what will finally be the thing that ends the mission? The event or the running out of gas? I mean, again, let's say if ideally, what will end the mission? If everything is going well, what will finally mean the end to the mission?
Well, ideally, yes. The propellant runs out. The attitude of the spacecraft can't be controlled anymore, so it shifts slightly and it starts to degrade because of all the radiation. That's what at least I am picturing being the end of the mission, but I don't know.
Yeah, I mean, this has been an extremely mass limited mission from the beginning. And that includes fuel. So we have, I don't know how much margin we have on our fuel, on the internal fuel that we use for correction maneuvers. But I imagine my bet's on the once the 7-year period is done, we'll do that. We've spec'd for that for sure. The duration of the mission will probably, the extended mission that is, will be dependent on how long the pointing systems last. Or, the solar arrays. If the solar arrays get destroyed for some process, or maybe they become less efficient over time and we don't have enough power, then we'll just turn off instruments, not mine, but.
Of course not. Right.
Of course not.
Yeah.
By that time, one or both, one of you will be NASA administrator, so that you can keep your mission going.
No,
right.
I mean, without Venus flybys, we can't really change our orbit significantly because we just don't have the propellant to do it. So it'll stay on that last orbit unless we get another Venus encounter. And then after it melts or fries or disintegrates, those pieces will stay on that orbit for a very long time.
And your prime mission is about 7 years. Did I hear that right?
That's right.
And where the prime mission begins is the closest approach.
No, actually, our prime mission starts as soon as we launch, I think.
Right.
Oh, okay.
Right. With every perihelion, starting when the first one in November, we talked about that at the top. That's the mission is going to be going ongoing while it gets.
That's T equals 0.
Right.
That's right. Yeah, and there's you think perihelion's really cool, and it is because we're closest to the sun, and actually. One of my favorite facts about the mission is we break the fastest vehicle record on our first orbit. The current fastest vehicle record's like 70 kilometers a second. And I think our first orbit, we get to 100. Our fastest speed is 200 kilometers per second. The last orbit is pretty sick.
Chuck Rittersdorf, there's the answer to your question. He was just asking that. Won't flying through the corona with such a high speed mess up your data collection? Will the PSP set a new speed record for a space probe? And you just said yes. So
yes.
There you go. So good one. Good.
But to answer his first question, no, I don't think. I mean, it will certainly distort our measurements to some extent, but we are prepared for that. That's what we're expecting to see. So it's certainly part of the mission to make these distorted measurements as we're flying at that high speed.
And part of it's kind of cool because, like, for our first orbit, we reach the same speed, the same angular speed as the sun itself. So we're sort of like, we're co-rotating with the sun for a short period of time, which is fun because we get to sit on top of sort of the same plasma source coming off the sun and measure it for a long period of time, which at L1, the plasma sort of passes over us as the sun rotates faster than that. So measuring for one spot will be pretty neat. And we do that the first orbit. So our prime science starts basically
right away.
Now.
Yeah, exactly.
Yeah. That's going to be amazing. Once we are essentially in the frame of reference of the plasma, it's going to be a whole new non-distorted measurement for the first time.
Good. Well, that was a good question, Chuck. And so I'm going to this is a good time for me to remind everybody that you can chat with our guests. Please leave questions. I've seen some of you now. I'm going to start asking them now. But please, you can do it on YouTube in the live chat. There's also the Discord server on deepastronomy.space/live. And here we are on Dark Time on the Discord server is asking, could a spherical ablative shield survive the flying fast through the transition zone below the corona, measuring temperature and magnetic field? Now, I should mention this isn't ablative, right? Ablative means that pieces of it burn off. Mm-hmm. Yeah, so it's not ablative.
Yeah. So no, this shield isn't ablative. Well, gosh, I hope not.
Yeah.
I guess if Roberto
that would be bad.
Lots of carbon, we'll know the answer to that. But yeah, so I think is this a question about like the concept of flying through the transition region?
Yeah, survive. Well, let's see.
Yeah.
Could these shields? He's asking about the shield specifically, flying fast through the transition zone below the corona, measuring temperature and magnetic field. So I think the answer is yes. It's designed to survive all of this. But what is the transition zone?
So the transition region is actually just above the photosphere. So transition. So the transition region, is that the region? I think that's the region between the photosphere and the chromosphere. There's like this very fast temperature increase between the photosphere and the chromosphere, but the chromosphere you're still really close to the sun within a solar radius, in fact. So the region that the Parker Solar Probe is going to orbit is actually through the sort of extended corona. So that's not quite the transition region. Now, on a separate aside, like ablative shields are really cool. I've seen them in concepts for like some really close sun missions, but I think that's a little outside the scope of Parker Solar Probe.
Right.
So.
Well, he's also got another good question. This is from Dark Time again. How does radio communication work when you're so close to the sun?
It doesn't.
Especially if you're behind the sun, there's no way to communicate.
Right. So when your deep space network time is well before, we were just talking about that. When you get your time, you don't want to get too much into the radiation of the sun.
Yeah, and part of the reason that we do that, I think, is because during that 10-day encounter period where we are close to the sun, the spacecraft's just sending a beacon saying, I'm okay, I'm okay, I'm not okay, I'm not okay. And that's all the data that we get. We hope not to get that I'm not okay signal. Yeah. But I think most of the processes on the spacecraft at that point are prioritizing making sure that the pointing of the spacecraft is correct and making sure that all of the science data gets written to the spacecraft recorder.
Yeah, good. Well, Galaxia's got a good comment where she says that they could also have called the Parker Solar Probe Icarus, which
I don't know about that. Because the end of that story is not very.
It's not. Well. But that does open the topic that we discussed briefly about who the probe is named after. It's named after a solar physicist named Gene Parker, and I don't know. Do we want to say a few words about who he is and?
Yeah, so Gene Parker was a scientist who first came up with, this involves a little bit of history, and I'll try not to go on at length, but before the first space probes with plasma sensing instruments were launched in the early 60s, the theory at the time was that the solar wind, this steady stream of particles coming from the sun, was actually subsonic, which means that it's traveling slower than the speed at which that waves can travel through sound waves. And Eugene Parker had this idea before any measurements were ever done that the solar wind was actually supersonic based on some math that he had done. And he tried to publish this paper. It took him a bit to publish it because everyone thought he was crazy. And the solar wind shouldn't be supersonic. There's no reason to think it should be supersonic. And it wasn't until the early space probes, some of them got out into the solar wind and measured the speed of the solar wind. And sure enough, it's supersonic. That crazy Gene Parker guy was right. And so he wrote this paper, I think it's 1958, that talks about this, made this prediction that the solar wind was supersonic. And in a couple other papers, he came up with some ideas as to what the acceleration mechanisms are, because this idea was so strange at the time. And now if you go through graduate school, everyone knows, oh yeah, solar wind's supersonic, Gene Parker, yeah, great. So it's really because of Gene Parker coming up with this idea of some mechanism must be heating and accelerating the solar corona to these huge speeds that now we have this field. And he really sort of is the father of that supersonic solar wind idea. And so it's really gratifying. Actually, Gene Parker got to see Parker Solar Probe. I actually took him into the clean room and showed him the spacecraft, and that was a pretty special moment. He was really excited, I think, about the mission.
Indeed, I think that's worth noting. He is still alive. He's getting pretty up there in years, and this is the first NASA mission named after a living scientist. So a little historical note there.
No, that's interesting. I didn't know that. Yeah, I guess things like with obviously Hubble, but things like Spitzer and Kepler, those guys are long gone. So yeah. Okay. Okay. Well, so a couple of, I think your cat wants attention there. Oh no, you jumped out. Okay.
It's gone.
Okay, so Hans Milling is commenting, I think they should establish a moon base and do exploration from there. Much cheaper to launch rockets from the moon.
That sounds great.
Yeah. So it sounds good. All right, well, let me just let me close up a little bit. When you guys, we still have some time for questions and comments, so please let them fly over here, and I'll read them out once I see them on these two methods here. So with the you guys are going to the launch, it sounds like, right? You guys are going to head down
That's right.
to Florida for the launch? Good.
It would be rude not to.
Yeah, it'd be rude. That's right. That's right.
Actually, then quick question. The launch vehicle has got an excellent record for launching on time. So what are the windows for its launch? If the mission gets scrubbed, as was the case with TESS, do you have a big window for subsequent tries?
I think the next opportunity to launch, if it doesn't launch July 31st, would be a year after. Is that correct, Phyllis?
No. Okay. So there's two parts, right? Our launch window is between roughly 4 and 6 a.m. Starting on July 31st, and then that window shifts forward slightly for about 2 weeks. I think we have about a 2-week period where we can rendezvous with Venus. And then at the end of that 2.5-week period, if we haven't launched, then we have another opportunity in 2019 to launch. So we have quite a long period of time during that launch window to launch. So I think the likelihood that we launch during that launch window is pretty high. I mean, no hurricanes, please.
No, right. I was just thinking of the New Horizons launch, which was postponed for I think almost a week. So
my gosh, no, don't say that.
Yeah, no.
Yeah, you're saying things that Phyllis doesn't want to hear.
Thank heavens you guys are not launching a Mars mission. If you miss your window, you got to wait 26 months for your next window.
Yeah.
Yep.
Andrew Planet posted a good the Wikipedia link about Gene Parker, so definitely go check it out.
He's something of a legend with good reason.
Yeah. So it's a good.
Brilliant
we're really looking forward to it.
And not just for solar wind stuff too. There's other aspects of space physics where he's a pioneer as well. So really remarkable man.
Right. Okay. All right. Well, I guess we will stop there. The Parker Solar Probe getting ready to launch July 31st, 4 a.m. From Cape Canaveral on a Delta IV rocket, which will be spectacular. I want to wish all of you, because I won't be around on April 24th, a happy Hubble anniversary. It'd be 28 years ago on April 24th that the Hubble Space Telescope launched into space, and it has enjoyed some of the most amazing science we've ever gotten out of a space telescope, but partly because it had been repaired 5 times. So most space telescopes don't get that luxury. So happy Hubble anniversary, everybody, on April 24th, and I'll be marking it with a Hubble margarita. I have a special recipe that I make with that. So
like a special glass?
No, it's
shaped like Hubble.
No, that's a good idea though. No.
Actually, there's an interesting point. Historical point. I was just thinking about this. Of course, NASA and the European Space Agency, the Japanese Space Agency, likes naming their missions after significant scientists. So we have, of course, Hubble and Parker, Chandra missions. All were University of Chicago professors or students. The Hale Telescope, also University of Chicago. Interesting comment.
Mm-hmm.
What do you say? Are you working for the University of Chicago now and recruiting for them? Is that what you're doing?
Actually, I think I am, because I graduated from there, and about every month I get a request for money.
Oh, I know. Yeah, tell me about it.
I think I am working for them.
I know. Yeah, the universities do that, don't they? Okay, guys. Well, I want to thank my guest, Dr. Phyllis Whittlesea. She's from the University of California, Berkeley, and Dr. Roberto Levy, also from the University of California, Berkeley, taking time out to talk to us about an amazing mission that's coming up, and we're very excited about it. So stay tuned. Space Fan News will certainly be putting some stories out on this as the time approaches. But mark your calendar for July 31st, and then again for November the following year, when it goes by the sun, or the same year when it goes by the first close approach to the sun, and then in 2024 it will get the closest anything has ever gotten to the sun. So we're looking
by a large factor.
By a large factor, that's right.
Yeah.
So
I think we break that record the first orbit.
Yeah. That's probably true. Yeah, I don't think.
And then again and again.
And then again. Just keep breaking it. All right.
Well, Messenger might have.
All right. So on behalf of Harley Thronson and our gravitational wave rubber ducky, whom we still need to get a name for, I want to thank you all for watching. And as always,